Okay, so fish enter a lake at a rate modeled by E of t. Fish leaves the lake at a rate modeled by L of t, given by this 4 plus 2 to the 0.1 t squared. Both E and L of t are measured in fish per hour. So both E and T are rates, right? These are both rates. And T is measured in hours since midnight. Okay, so the assumption is that there's no fish to begin with at the lake, and then as they start coming in after midnight, then we can kind of keep track of the numbers. Okay, so part A, how many fish enter the lake over a 5-hour period from midnight to 5 a.m.? Give your answer to the nearest whole number. So we know that E of t is fish per hour. So if I want to find the total number of fish in that 5-hour period, I would have to convert this fish per hour to be in terms of fish. So I have to take the antiderivative, right? We can accumulate the rate over a 5-hour period, and then we can find the accumulation of those fish per hour coming in to the lake. So we can simply rely on just definite integral from 0 to 5 of E of t dt. Okay, let's practice entering this into our calculator. You want to make sure you're in radian mode. So because if you're using graphing calculator, it's just more efficient if you put your function, especially a messy function, into y1. That way, if you're having to call it later for graphing or for integral or for derivative, you don't have to keep typing this in every single time. You can just reference it under y1. Okay, so the referencing it is vars, y vars, function y1. Okay, so I have that under y1. I'll do math 9. Take me to my depth integral from 0 to 5 of my E of t function, which is stored under y1. Round to the nearest whole number, so 153 fish. Okay, part B. What is the average number of fish leaving the lake per hour? So we want to find the average fish per hour, basically find the average of this L of t. We want to find the average of L of t. L of t is in fish per hour, so we want to find the average value of L of t over that 5-hour period. So average value theorem. Okay, average value theorem, 1 over b minus a, definite integral from a to b of f of x dx. That's the formula. And we can adapt it for L of t. My a is 0 and my b is 5. And make the calculator do the work for us there. Okay. So what I did was I had y2 hold my L of t function. And I just did math 9 for that integral. So my average value of the rate that fish is leaving the lake is 6.05 fish per hour. That's the average per hour in that 5-hour period. Okay, part C, at what time t is the greatest number of fish in the lake? So greatest number, this is telling us to apply what? All right, anytime we're looking for absolute max, absolute min, we're looking to use extreme value theorem, right? So extreme value theorem says we got to test endpoints and we got to test critical points. So before we can test endpoints and critical points, we first have to have a formula to figure out, how do we find the number of fish at any given time? So this is the formula that we've been using when we first started AP exam review. Remember the problems involving people entering and leaving an amusement park, sand being added or removed from the beach, right? So we use this formula over and over again here. So total amount is initial amount plus amount added minus amount removed. So this allows it to kind of keep track of all these moving parts. All right, so if I want to find out the total amount at any given time, I first need to know how much did I start with, how much has been added in that time period, and then how much has been removed in that time period. And that will get me to the number, the remaining portion. Okay, so we're going to build our formula. Okay, so we'll let f of t represent the total number of fish at any given time. Our starting number is f of 0. The amount added would have to involve e of t, but it has to involve an integral, right? Because we know that e of t is fish per hour, which is not the total number. We got to take the integral of that e of t to get it up to a number. So, but we want to keep the flexibility of allowing for any time that we're asking for later. So we do the integral from 0 to t of e of x, and that will give us that flexibility, whether I want to find the total number of fish in the 3-hour period or 5-hour period or 6-hour period. I give myself that flexibility for to adapt to future situations. I'm not locked into just one value. Okay, but I also want to figure out how many fish has left. So I need to remove that from the lake. So minus 0 to t of L of x. So that's the formula that will tell me the number of fish at any given time. Right. So we need to build that, know how to build it, starting from this this formula that we see in these types of problems. Okay, any questions so far? Okay, so this is how we can find the total number of fish at 0 and 8, because we definitely need to test endpoints. But how do I go about finding my critical point? Critical point comes from where? Maybe not the function, but the what? Or in general, how do we find relative max and relative min? How do you go about finding these critical points? Set what equal to 0? Derivative, right? So we have to find the derivative first and set equal to 0. That's right. So we need to set the derivative equal to 0. Right, that's a process for EBT there. So we need to find f prime, set f prime equal to 0. So f prime, that just becomes f prime of t. F of 0 is just a number, so that number is going to go to 0. So there's no need to worry about this f of 0. But what's the derivative of the antiderivative of e of x? What's going to happen here? Yeah, it'll cancel each other out, right? The derivative of an integral is going to bring it down to, so right now this expression is sitting one level above e of t. If I find a derivative, I can bring it back down. So this becomes e of t. And the derivative of this antiderivative will bring this down to L of t. So there's my derivative, E of t minus L of t. And I want to find a critical point, so I'm going to set that equal to 0. So the strategy here is we're going to graph this E of t minus L of t graph and see where it crosses the x-axis. And that will tell us the solution that we're looking for, or that will tell us the critical point that we're looking for. Okay, so we're going to graph this. E of t minus L of t. So I have y1 holding my E of t. I have y2 holding my L of t. And I'm just going to do y1 minus y2. That way I don't have to keep entering. I'm going to unhighlight these equal signs as well. I just want this y1 minus y2 to show. So I'm just going to have y3 show me the graph. And I'm going to unhighlight y1 and y2. Okay, go to window, make some adjustments here. We know that our critical points has to live between 0 and 8. So I'm going to adjust my t values here, or my x values between 0 and 8. And maybe I'll just go from -10 to 10 just to see how my graph looks. Okay, so there's my one critical point. Okay, so do second trace, 0. Left bound, I can choose a value. To the left of my x-intercept, hit enter. Choose a point to the right of the x-intercept, hit enter. And that'll give me 6.203. So that's my critical point. I know that that's the only critical point that I have. So I have 3 points to test. I need to figure out how many fish is at 0 hours, how many fish is at 8 hours, and how many fish is at 6.203 hours. Okay, so we just take our time entering into our f of t. We know there's no fish to begin with, so f of 0 is going to be 0. F of 6.203, we can enter them into the calculator one by one, right? Figure out how many fish has come into the lake in that 6-hour period, but then we also need to subtract out the number of fish who's left in that 6-hour period as well. So here's my work, or here's my process of entering in. So I did the integral from 0 to 6.203 of my E of t function, which I'm holding under y1, and I'm subtracting the number of fish who's left the lake. Y2 is holding my L of x, my L of t, 135. Okay, repeat the process for 8 hours. So I can just go back to my previous entry and then just change my upper bound from 6 to 8. So between these three, we're looking for when is there going to be the maximum number of fish, and the maximum number of fish is going to occur at 6.203 hours, 135 fish. And your justification is showing your steps for EVT. You don't have to mention EVT, but you just need to show that you are testing endpoints and critical points, and that you are actively finding those values, and that you're actively comparing them where the maximum is going to be. Okay, part D is the rate of change in the number of fish increasing or decreasing. So what is this referring to? We know that the rate of change in number of fish, that's dealing in terms of LFT and EFT and LFT. What is this increase decrease is gonna, what's that gonna do to what's asked of us? Involving the what? That's right, yeah. So anytime you see increase decrease, and it's describing something that we know is going to be a derivative or rate of change of something of what's here. So this is sitting at the F prime level, right? F prime is EFT minus LFT. So if I want to do the increase and decrease of this rate, then it's going to take me to the second derivative. So here's my second derivative. Just make everything go down one level. F prime becomes F double prime, E becomes E prime, and L becomes L prime. I want to find out the rate at which fish is either leaving or coming in. You know, rate of change in terms of is the number, is the rate increasing or decreasing? We can simply go through and plug in 5 into my formula. So E prime of 5 minus L prime of 5. We can make the calculator do this for us. Remember, our n derivative feature allows us to find the derivative at a point. So do math 8. D over dx. Type in your EFT function, which I have stored under y1, and then ask it to find the derivative for you at 5. Repeat the same process for, I have my y2, which is storing my L of t. Okay, so there's my E prime minus L prime, negative 6.8 minus 3.92. That gives me negative 10.7227. This is now in terms of fish per hour squared, or fish per hour. And we know the rate of change is decreasing. So this is the way that you want to reference the second derivative. Okay, we don't want to just say acceleration, right? That's not going to make sense in this context. And also, the rate of a rate is not descriptive enough. But if you say the rate of change is decreasing, then you're showing that you're able to verbally describe it in a way that will earn you points for justifying your answer, and you're also making it clear that you're understanding that it's the rate of change that's decreasing, right? So just be comfortable with those words, especially when there's a second derivative involved. Okay, let's go to number 2. Page 10. Okay, velocity of particle P is moving, sorry. Okay, velocity of particle P is moving along the x-axis as given by a differentiable function. Again, smooth curve, no sharp turns, no holes. V of t, you see that subscript P just means that it's talking about the velocity function for particle P. Usually they do this if there's another velocity function defined, which we're going to see later. So that's just telling us that that's velocity function for particle P. Measured in meters per hour and t is measured in hours. Selected values of velocity are shown in the table, and particle P starts at the origin time t equals 0. Okay. Justify why there must be at least one time t between 0.3 and 2.8 where v prime, the acceleration of the particle p, is equaling to 0. Okay. Trying to figure out where v prime is equal to 0 and justifying or guaranteeing that time. Does that remind you of any theorem that they're trying to get us to reference? What if I said it this way? V prime is another way of saying slope of v of t. Trying to figure out when is the slope equal to 0. Does that ring a bell? What can we use to guarantee where slope is 0? Remember a particular theorem that involves slope zeros? Yeah, not mean value theorem, but Rolle's theorem, right? Rolle's theorem says if I have 2 points that are at the same level, then we know that somewhere between it's got to go up and come down to that level, or it's got to go down and come up. In that process, it's going to have to hit slope 0, especially if we're dealing with a smooth curve. So with Rolle's theorem, we need to confirm that our function is continuous and differentiable, which it is. And we also need to confirm that our endpoints have the same y values, which they do, right? So if we're starting at height of velocity 55, it goes down to negative 29 and comes up to 55. Along that way, the graph is going to go down, come up. In that process, there must be a slope 0 in my velocity graph. Okay, so I should have to be able to write that out. So by Rolle's theorem, since my velocity is continuous and differentiable, continuous, close bracket, differentiable, open parentheses, and we have our endpoints giving us the same velocity, then there must exist at least one other time, or one time where my v prime or my acceleration is equal to 0. Okay, part D. Use trapezoid with trapezoidal sum with 3 subintervals to approximate the value. So trapezoid, again, the formula is 1/2 width, height 1 plus height 2. We're going to do this for 3 separate regions because we have most likely 3 separate trapezoids of different widths. Okay, so we go to our table. We subtract our subintervals and to get our width. So 0.3 minus 0 is 0.3. 1.7 minus 0.3 is 1.4. 2.8 minus 1.7 is 1.1. So the width is going to come from this highlighted orange that I have here. And then your height is going to come from this velocity. Okay, so we're just using these numbers to create our width and height to build our area of trapezoid. Okay, so let's see if we can do that. Okay, so first trapezoid, width of 0.3, height of 0 and 55. So we add those together with the 1/2 in front. Okay, great, thank you. Okay, we go down the line, finish off the rest of our trapezoid area formula. Now, I want to point out, I saw this on the previous quiz that you guys took, where I saw some students subtracting the heights for trapezoid. We always are adding. Okay, we're always adding, but it does look like we're subtracting here. But it's because there's a negative as one of the heights, so that's why there's that negative 29. But typically, we don't think in terms of subtracting. Okay, we're adding a negative number, so that's why it shows up as negative. But this kind of reminds me that I saw some students actively subtracting the heights, and we want to just follow the formula as it is. We want to add the two heights together. Okay, so this tells us how far particle P has traveled in that 2.8 seconds, right? Okay, good. Part C, any questions so far? Part C, a second particle moves along the x-axis so that its velocity is given by VQ of t. So this is referencing a different velocity function with that subscript q in meters per hour. Find the time interval in which the velocity is at least 60 meters per hour. Find the distance traveled by the particle in that time interval. So this is what we're trying to achieve here. We're trying to figure out when is my velocity going to be greater than or equal to 60. So that's my goal. All right. So how can I use my calculator to help me out here? Well, I can graph both 60 and velocity and see where they intersect, but it just seems like it's going to have to do a lot of adjustment with our window to get it to show that 60. So would it be easier then to subtract that 60 and just look to see when is this curve going to be above the x-axis? And then we can figure out where that time interval is, and then we can go from there. Okay, so we'll do v of t minus 60. So I'll have it stored under y4 here. This is my v of t, and I'll go ahead and subtract 60. And I'm going to adjust my window. Okay, so my window, I know that I'm looking at only values between t values between 0 and 4. So I'll adjust my interval here from 0 to 4. Now, as a frame of reference here, I know it's a different particle, but I see that my particle here, my velocity is all the way up in 50s range. And then also my function has that 45 in it. So kind of gives me a feeling that negative 10 and 10 is going to be a little bit too zoomed in. So I want to just give myself that flexibility. I can always come back and change it. But I'm guessing that, because these two particles are probably within the same vicinity. So I'll say negative 50 to 50, just see where that, and I'm just looking for x-intercept. Where is the graph going to live above the x-axis? Okay, so that's the region that I care about. I care about this region where it's going to be greater than 60, because we made that adjustment. Okay, so look for that x-intercept. We can do second trace, find those two x-intercepts, and we know what's between those two time values is when my particle is going to be moving more than 60. Second trace 0. Choose a point to the left of the x-intercept, hit enter. Choose a point to the right of the x-intercept, hit enter. 1.866. Do the same process for my other x-intercept. Scroll over. Hit enter. Other side, hit enter. 3.519. Okay, so there's my two time intervals there, between 1.866 and 3.519. So the next part is asking, find the distance traveled between these two time intervals. So we can just take the displacement, right? The integral from 1.866 to 3.519. Now you may be asking, wait, distance, don't I need the absolute value? You could definitely use absolute value, but we know that our velocity is already cleanly sitting above the x-axis, so we're not gonna have to adjust any negative velocity here. Everything is cleanly above the x-axis, so I just didn't use the absolute value. Okay, part D. At what time t equals 0, or sorry, at time t equals 0, particle Q is at position x equals -90, so it's all the way over on the x-axis, all the way over at -90. Using the results from part B and the function from this velocity for particle Q, approximate the distance between particles P and Q at time t equals 2.8. So why don't we do this? Why don't we spend the time to figure out where is particle P at 2.8? Where's the particle Q at 2.8? And then once we find their positions, we can look at the distance between them. So anytime I have velocity starting point, I'm going to use this formula here. Final position equals initial plus displacement. And we'll do this one particle at a time. Okay, so we'll start off with particle P. So if I want to find particle P's location at 2.8, that's my goal. I'm going to set that to the side. Equals x of 0. X of 0 would be where's the particle beginning at 0 seconds? And then how far does he travel in that 2.8 second period? Well, if you look at the top of the page, particle P is at the origin at t equals 0. So that's, we know x of 0 is 0. And then the integral from 2.8, we gather that from part B. Part B, using trapezoidal approximation, we figured out how far he traveled in that 2.8 second period. And then we can add that to 0. So that means we know this particle P 2.8 seconds in is located at 40.75 on the x-axis. Okay, we'll do the same process to figure out the location for particle Q. So particle Q, for part D, they tell us that particle Q is located at -90. So we know that he starts off at -90. But now we got a formula to plug in. So we'll do the depth integral from 0 to 2.8 for velocity for Q of t. Figure out how far he travels using the calculator, and then add it on to that -90. And I get 45.9376. So now we know where the particles are located 2.8 seconds in. We can just subtract that distance to figure out what separates them. Approximate the distance, we just subtract those two numbers, those two locations. We know they're about 5 meters away from each other. Okay, questions so far? Okay, let's start a little bit into number 3. Okay. This is now this begins the non-calculator portion. Okay, continuous function f is defined on a closed interval from -6 to 5. The figure shows a portion of the graph of f consisting of 2 line segments that we see here, 2 line segments, and a quarter circle centered at 5, -3. So you kind of imagine that, you know, there's a quarter circle here. It is known that the point 3, 3 minus root 5 is located on the graph of f. So probably this point right here, which we'll come back to later. So part A says the full region from from -6 to 5. Now there's a whole portion that's missing, right? But we know that the entire definite integral, totaling all the positive and negative values, is going to be equal to 7. Okay? It says find the value from -6 to -2. So it's asking for this unknown region. We have the full region. We have this portion we can find out, and if we subtract those two, we should be able to get to this missing piece. But let me build a equation so we can see all the parts that we're working with. We know that the full region from -6 to 5 can be broken down into the known and unknown, or the seen and the hidden. So the hidden portion is from -6 to -2. And the revealed portion is from -2 to 5. But if we look at this, we have the entire region accounted for, right? We're splitting them up so that we can strategically look for the ones that we're missing and filling in the parts that we were able to find out. So let's spend the time to figure out the definite integral from -2 to 5. These are all geometric shapes, or combinations of geometric shapes. And we want to keep add up all the triangles and shapes involved. Anything above is positive, anything below is negative. So these are the regions that I care about. It's between the graph and the x-axis. So the question is, there's a triangle, 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 but how can I find this region? It's not a geometric shape by itself, but is this a combination of geometric shapes that we can arrive at? What do you guys think? Yeah. What can we do to get to that, this kind of funny looking shape here? Where is it coming from? Yeah, circle and square, right? So I can take the area of a square, subtract out the quarter circle, and what's left is this leftover region, right? So that's the strategy to get to that kind of undefined geometric shape. So square minus a quarter circle. So the square is 3. Width times height is 3 squared. 1/4 pi radius squared. So that region is going to be 9 minus 9/4 pi. Okay, I'm just going to total all these areas here. Here, this is going to give me a positive 1/2. This here is negative 1/2. This here is negative 1/4. This here is positive 1/4. This triangle up top is going to be 1. And this square is 1. So all this is going to represent this portion here. I know that the integral from -6 to 5 is 7. So I can subtract that out and isolate and get this by itself. Let me show you my work for that. So this is the result of me adding all those individual geometric shapes that I have. The portions above and below the x-axis cancel each other out nicely. So the 1/2, the -1/2, the 1/4, -1/4. And then the last two parts are the remaining triangle, square, and then the square minus semicircle. So everything is accounted for. The only thing that's left standing is the missing integral value that I'm looking for. So I can just get that by itself, subtract the 11 and add the 9^4, and I get 9^4 minus 4. Okay, so your homework is pages 9 to 14. He is on the website, and I will do a help session this afternoon to go over the rest of this year's FRQ 3 through 6.